Okay guys, today we're going to start the next unit on chemical reactions. In this unit we're going to learn about chemical reactions and how to write chemical equations. Okay, so first off, what is a chemical reaction? A chemical reaction is a process where one substance or more than one substance changes into something else. So when I say they change from one thing to something else, that means we need to break and form new chemical bonds. So if you look at the chemical equation on the bottom, that shows two hydrogen molecules and one oxygen molecule. And on the right-hand side of the arrow, you see two water molecules. In order to turn the oxygen hydrogen into the water, we had to break the hydrogen molecules apart and the oxygen molecule apart and form new chemical bonds. That's what a chemical reaction is. There's a video there if you guys want to watch a little video on chemical reactions. Now, there are some indicators that can tell us when you're in the lab if a chemical reaction has occurred or not. We talked about these earlier in the year. They are a change in temperature. So, for example, an ice pack, when you crack the ice pack or you start a fire, heat gets released or heat gets absorbed. Heat getting released or absorbed is an indicator of a reaction. By the way, these are just indicators. I'm not saying if one of these happens, you automatically assume a chemical reaction has occurred. They're indicators. They help you determine whether or not a reaction occurred. Second one is light is released. For example, when you crack a glow stick, the chemicals mix, creates a chemical reaction, and releases light. Or a lightning bug. Summer's going to be starting soon. You'll start seeing lightning bugs out. They do something called bioluminescence. They mix some chemicals which generate some light. Fireworks, same thing. Any kind of light getting released. Next one, the formation of a gas, which generally, if you're in the liquid state, you see bubbles being formed. So if you mix baking soda and vinegar together, as you can see in the picture in the bottom left, it produces a lot of bubbles. Those are carbon dioxide. It tells us carbon dioxide was released from the original baking soda molecule. Okay, what about boiling water? When you boil water, you see bubbles. Does that mean it's a chemical reaction? No. Remember, these are just indicators. Boiling water is a physical change from liquid water to gaseous water. It's still water. We didn't actually break any chemical bonds. So just because we saw bubbles does not necessarily tell us it's a chemical reaction. Next one would be the formation of a precipitate, which we call a solid. You guys have seen this in the lab thousands of times this year. The picture on the bottom left with the yellow cloudy looking thing, that was when you guys did this earlier when you mix lead nitrate and potassium iodide together. The nitrate and the iodide switch positions and you form something called lead iodide, which is that yellow solid cloudy looking thing. Okay, and then the last one is a change in color. Same thing. We just mixed lead, nitrate, and potassium iodide. I'm going to use the same example again. They started as two clear liquids, and they made a yellow substance. That's an example. Okay, what about if we put food coloring in water? Is that an example? No. And the reason being is you're taking like a blue food coloring and putting it in water. You're just mixing it up. You're creating a mixture. You didn't actually turn the water into something else. You just put something blue in it and it just gets diluted in the water. So I want to make this clear. Those phase changes we talked about earlier in the year, melting, freezing, evaporation, condensation, sublimation, deposition, those are physical changes, not chemical reactions. Okay, now that we know kind of a basic idea of what a chemical reaction is, we have to represent them using what are called chemical equations. So you guys have seen these throughout the year. Chemical equations are how we represent a chemical reaction in shorthand notation. You could always write them out in sentence format, but it's much more concise and easy to read in chemical equation format. Now, chemical equations have a couple different components that we need to discuss. Okay, so I want you guys to actually label these on this example in your note packet. The substances on the left-hand side of the arrow are called the reactants, and the substances on the right-hand side of the arrow are called the products. The little numbers down low, the little tiny numbers, those are called subscripts. You guys know all about those. And then the big numbers, like the 2 next to the H2O, that's called a coefficient. Okay, so reactants are the things that are present at the beginning of the chemical reaction. They react together. Now, when I say they react, what does that mean? It means that their chemical bonds are broken. Not necessarily every single chemical bond in the substance, but at least some chemical bond in each one of the substances that are in the reactants gets broken apart. Okay, so in the picture at the bottom of the page, we have methane and oxygen reacting together. The methane loses all 4 of its hydrogens, and both oxygen molecules break in half. So in this case, all the chemical bonds are broken. The products are found on the right-hand side of the arrow. Those are the things that are formed during the chemical reaction, meaning new chemical bonds are formed in order to make these substances. So in the case in the picture on the bottom, we're making carbon dioxide and water whenever you start a fire. Okay, so let's relate this to everyday thing. Let's say you were building a model car. Let's say that toy model car had one car body, 4 wheels, and 4 doors that you need to put together. If you want to represent the building of that car as a chemical equation, you would write one body plus 4 doors plus 4 wheels equals, in this case we're going to use an arrow, one car. By the way, I'm just going to say this right now. An arrow does not mean an equal sign. It means that the things on the left turn into or form the things on the right. It's not necessarily that they're equal to each other. It's not the same as math class. It means they turn into. Okay, so in this case, the body, the wheels, and the doors are the reactants, and the car is the product. Okay, so the subscripts, which you guys know all about, so I'm not going to spend any time on this. The blue 2's in the picture at the bottom, those are called subscripts. It tells you how many of that atom you have. So 2 hydrogens, 2 oxygens, 2 hydrogens. Okay, so some examples. Again, you guys already know how to do this, so I'm not going to spend any time on this. C2H4 means you have 2 carbons, 6 hydrogens. Ca3PO42, in this case, we had a parenthesis, so don't forget you have to distribute the 2. So we have 3 calciums, 2 phosphoruses, and we have 8 oxygens, 2 times 4. So again, just make sure, this is going to be very important later in this chapter when we have to do what's called balancing the equation. You have to distribute that coefficient, or sorry, that subscript if it's on the outside of a parentheses. Okay, so coefficients are the ones that are kind of new to you guys this chapter. Coefficients are the big numbers that are found in front of the substances that are participating in the reaction, or they could also be the products. Okay, so if you look at the example below, it says 2H2 plus O2, arrow, which means to form, 2H2O. So what does this mean? It means that 2 hydrogen molecules react with 1 oxygen molecule to form 2 water molecules. So the coefficient tells you how many of that molecule or substance you have. Now, I just want to note real quick, we're not going to do this right now, but how many hydrogen atoms do I have on the left-hand side of this equation? I have 4, because if you notice, each hydrogen molecule has 2 atoms in it, and I have 2 of them. So 2 times 2, I have 4. If you look on the other side of the equation, I also have 4. I have 2 water molecules. Each water molecule has 2 hydrogens, so 2 times 2 is 4. Okay, that's going to be important later in this chapter when we do what's called balancing the equation. Now, I want you to notice in front of the oxygen, there's no number. If you write no number, that just means a 1. In chemistry, again, we just tend not to write 1s. It's more work. If you want to write the 1 to make it easier for you, you can. It's just not necessary. Okay, some symbols you guys are going to see throughout this chapter and just throughout your life is relating to chemical equations. Arrows, again, means to yield, to form, to produce, not equals. Sometimes you're going to see little subscripts. We're going to use them in a second. Parentheses S, parentheses L, that's an L, not an I, and parentheses G. That indicates that the substance is a solid, a liquid, or a gas. So if you look at the example over here, it says Fe, parentheses, S, parentheses. That means this is solid iron. If you change it to an L, it would mean like molten iron, like liquid. Okay, the other subscript you're going to see occasionally is AQ. AQ stands for aqueous. Aqueous, if you guys remember from earlier in the year, means dissolved. So if you have NaCl, aqueous, that means salt water. So it means you have salt that's dissolved in water. Plus signs just mean to react with. Sometimes you're going to see a double-sided arrow. Double-sided arrows mean the reaction can go both directions. So not all reactions are irreversible. Sometimes you can go both directions, back and forth, depending on the conditions. The bottom two we're not going to see too often, at least in this class. If you guys are going to take AP Chem, you will see a lot of these. Sometimes chemical reactions need heat to get started, like a fire. You need heat to start the fire. So oftentimes they write either a delta sign, which is this little triangle, or just the word heat. That means heat is added to the reaction. And then lastly, sometimes something called a catalyst is needed to start a reaction to make it speed up. In this case, it's palladium. So if you see a symbol of an element over top of an arrow, that just is called a catalyst. We're not going to deal with those at all in this chapter. Okay, so I was just talking about catalysts are things that speed up chemical reactions, but they don't get used. You guys learned a lot about these last year in biology. These are your enzymes that help break down your food and build your DNA and build your proteins and so on. Okay, last thing I want to talk about for this lesson is what's called a skeletal equation or skeleton equation. Skeleton equations are equations that indicate the types of substances that react with each other and are formed, but it does not indicate the amount of them. So basically, we're going to use no coefficients in these examples. So if you look at the example at the bottom of the page, that equation should look familiar to you. You guys learned it last year in biology. It's called cellular respiration. It says glucose reacts with oxygen to form carbon dioxide and water. So that's you guys breaking down your food and breathing out carbon dioxide and water. So if you look at that equation, it doesn't tell you how many glucoses I have, how many oxygens, how many carbon dioxides, how many waters. There's just a one coefficient in front of all of them. Now, in real life, there would be coefficients there, and we're going to deal with that later, but for right now, I just want to learn how to do the skeleton equation. Okay, so let's just do a couple examples. So we're going to take a sentence and turn it into a skeleton equation. So it says solid iron reacts with oxygen gas to produce solid rust, which is iron 3 oxide. Okay, so when you write this down as an equation, you write Fe with a parentheses S, that means solid. This is a subscript, by the way, so it should be down in the bottom right-hand corner. Reacts with this, the plus sign. Oxygen gas is O2, parentheses G. And then to forms is the arrow. And then this is rust, iron 3 oxide, Fe2O3, and rust is a solid, so we put the little S there. Now again, we're not having any coefficients. No coefficients in these examples. Okay, example 2. Aqueous hydrochloric acid reacts with solid sodium bicarbonate to produce aqueous sodium chloride, liquid water, and carbon dioxide. Okay, so HCl is a hydrochloric acid, and it's aqueous, which means it's dissolved in water, so we write AQ. Reacts with is the plus sign, sodium carbonate or bicarbonate, which is baking soda, NaHCO3, and we know it's a solid, so we put a parentheses S. Okay, forms is the arrow, salt, which is NaCl, and we know it's aqueous, which means it's dissolved in the water, so AQ, plus water, H2O, and it's a liquid, so you put a little parentheses L, and then plus carbon dioxide, CO2, and we know it's a gas, so we put the G. Okay, example 3, solid sulfur burns an oxygen gas to form gaseous sulfur dioxide. Okay, so solid sulfur is S with a little subscript of an S, plus O2, little g for gas, forms SO2, and we know it's a gas. Okay, and then the final example, solid sodium reacts with chlorine gas to produce solid sodium chloride. I showed you guys this video earlier in the year. Sodium and chlorine gas will actually create a huge explosion, and it just makes table salt. So solid sodium reacts with gaseous chlorine to form solid salt, NaCl. Okay, now, the equations we just wrote, they are not actually correct. We're writing them right now just to give you guys an introduction to writing chemical equations and learning what all the pieces mean, but they're not correct because if you look at the equation above, if you look on the left-hand side, we started with 2 chlorine atoms. Look on the right-hand side of the equation. We only have 1 chlorine atom. Atoms cannot just disappear. Matter cannot be created or destroyed. So this equation is not truly indicative of what happens in this equation. It's not balanced. And we're going to learn how to do that later on, like next week. So I'm not going to deal with that right now. I just want to mention these equations are not totally correct, but they give us an idea of what is involved in the chemical reaction. Okay, now sometimes you guys are going to be using a lot of the same molecules, and the molecules you guys can use all the time are called diatomic molecules. I mentioned these earlier in the year. They're molecules which always consist of 2 of the same element. I want you guys to try to memorize these. They're not that hard to memorize. I know it looks like a lot. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. If you guys pick up your periodic table right now and you look at it, the nitrogen, oxygen, fluorine, chlorine, bromine, iodine are going to make a 7 in the top right-hand corner of the periodic table, not including the noble gases. Hydrogen's kind of the oddball as always over in the top left-hand corner, but these are the gases which always form diatomic molecules. If you draw out their Lewis structures, you'll see why they always form diatomic molecules. Okay, there's a couple of review questions. I think there's like 4 of them in the note packet following this part in your notes. I want you guys to answer those questions. You're going to have to draw a couple skeleton equations. If you guys have any questions, let me know.